Welcome back to sections 10.1 through 10.3. In this video we'll be going over example 2, which will show us how to calculate the radius of gyration for the area moment of inertia. So radius of gyration is just an alternative measurement. It's also a measurement of how easy it is to bend something in this case. If you were doing it for a mass moment of inertia, it would be difficulty to accelerate or rotate. But again, we're concerned with area moments of inertia. So this value, which is commonly a k, even though it's a radius, it's commonly a k, at least in the book that we're using. That'll be the difficulty of bending something, so larger means more difficult. So we're going to use example 2 for that. So example 2 looks the same, except we're going to do this about the x-axis this time instead of the y-axis like we did in example 1. So I've copied the problem over here. We're asked to find kx. So there's a relationship between radius of gyration and area moment of inertia. So kx can be calculated as the square root of ix divided by a. Normally you're not going to be asked to find the radius of gyration for a shape, but you may be given the radius of gyration. So if you have a complex shape in a problem, they may tell you what the radius of gyration is, and you have to convert it over. In that case, you would say, oh, it is kx squared times area. So that way you can convert for complicated shapes to a area moment of inertia, which is very useful. But we'll go ahead and calculate it for this problem. So that means the first thing we're going to have to do, so we know that we have kx is going to be equal to ix divided by a, and we're going to take the square root of that. So we need to find ix and a. So let's start off by finding ix. Ix is going to be the integral of y squared dA. So just like last time, we'll make a differential area. This time we're going to measure up to it from the x-axis. So we're going to have our y direction. We still have our dy. We still have our dx. The integration is going to be the same set, so we still want to go from y equals 0 to y equals x to the 2/3 for the same reason as problem 1. It's nice to start off with that y equals 0 down here. So we will integrate from y equals 0 to y equals x to the 2/3. So we'll get a y squared, and then we're going to go dy dx. That has nothing to do with this being a y, by the way. And then we will go from 0 to 1. X starts at 0 and goes to 1. So you do that, you get a 0 to 1, you get a y cubed over 3, and then we get an x to the 2/3 to 0. So that x to the 2/3 is going to come in here for the y. The 0 is just going to go, and nothing's going to happen with that. You will end up getting a we'll get an x to the 2/3 raised to the 3rd power all over 3. And that'll simplify down into an x squared over 3. And it's all over 3 dx. So when we finish up this, we will get x to the 3rd over 3 times 3, which is 9. So we'll get 1/9, and that's meters to the 4th power. So it's 1/9. So if we pause for a second and we think back to what we had for our previous problem, that was 3/11. So 1/9 is like 0.1 repeating. So we have a much larger value. So this is much more likely to bend about the x-axis than the y-axis, is what that means. So if I was going to bend this shape, say this shape was extruded, it would bend much easier about this x-axis. So kind of like this bending versus this bending. All right. To continue finding this, I have to go find the area. So to find the area, we're just going to integrate dA. So same integration, 0 to 1 for x, 0 to x to the 2/3, and then we're just going to go dy dx. Nothing else inside. So end up with 0 to 1, and then I'll have a y, x to the 2/3, and a 0. This will become just an x to the 2/3. dx, when you integrate that, you will get an x to the 5/3 from 1 to 0. So we get 3/5 of a meter squared for our area. So if I bring all that back, oops, sorry, you couldn't see that, 3/5 of a meter. So if I bring all that back up here, then I will get 1/9 divided by 3/5, and I'll take the square root of that. So you just plug that into your calculator, and you will get 0.430, and the units on this is just meters. So what this is simulating is if I took a mass, an area, so a concentrated area, and put it 0.43 meters away from the x-axis, that would do the same exact thing. If you wanted to turn it into a circle, so like say I wanted to have a circle of certain radius that had the same value, this would just be basically 2kx. 2kx, if you want to kind of visualize what it looks like. So a circle that has 2kx in area should have the same same area moment of inertia about its center. So how hard would it be to bend about that x-axis? All right, so hopefully that helps. If you have any questions, feel free to reach out.